All right, I was assigned problem 23 in chapter 2, and this question asks us to prove that the divergence theorem, or to prove the divergence theorem for several scenarios. So part A asks about a cube with side length of b. So this is the divergence theorem right here. We're going to need to prove that the surface area double integral is equal to the volume triple integral. So to start with, let's look at the volume. We're going to want to come up here to what they give us. They give us the vector field is equal to x I hat plus y j hat plus z k hat. And we know that the divergence of this vector field is going to be equal to the derivatives, the sum of the derivatives. So and this is also actually going to equal del dot f. So if we solve this out, it's pretty simple. This derivative is going to be 1. This derivative is going to be 1. This derivative is also going to be 1. So if we take that here, we are going to find that 1 plus 1 plus 1 equals 3. And this is also going to be del dot the vector field again. The next step we're going to want to take is to integrate it. So we're going to do integral from 0 to b, integral from 0 to b, integral from 0 to b. This is 1 for each side, so it's going to be 1 for y, 1 for x, and 1 for z. And then we're just going to put 3 dx, dy, dz. So we can start to simplify this. We will get integral from 0 to b of the integral from 0 to b of 3x 0b dy dz, and this can be changed into 0b 0b 3b dy dz. We're just going to do the same thing 2 more times, so it's going to be equals, I'll save the extra step and go 0 to b of 3b squared dz, and then this is going to turn into 3b cubed, and this is going to be our triple integral for volume of del dot f dv. So we'll make a note of that. Next up, we're going to have to do this side of the equation. So moving on, the way this one's going to work is that conceptually we're going to want to add the sum of side 1 plus, or the integral, of side 1 plus the integral of side 2 plus the integral of side 3 plus the integral of side 4 plus the integral of side 5 plus the integral of side 6. This will make up the surface area vector, or the surface area integral. Fortunately for us, the field is coming radially outwards from the origin, so it's going to be going up the z-axis, up the y-axis, up the x-axis, and it's going to be coming out like a sphere. So what that means is that this left side, this back side, and this bottom side are all going to be parallel to this vector field because they are on coordinate planes. So if you think about it, all these vectors will kind of come out here, will come out here, come up here. They'll be different, but they'll all be parallel to these three sides. So that makes it nice and easy because this is going to be 0, this is going to be 0, and this is going to be 0. So the sides we're going to be looking at are the top, the right side, and the front side. So over here, we're going to have x equals 0, x equals b, y equals 0, y equals b, z equals 0, z equals b. So all of these 0 functions are the ones we just crossed off right here. So what we're going to want to do is, or what I did at least, was essentially cast or project this surface right here down onto the xy plane. So what that would look like is that's going to be integral of s of f dot n hat ds equals s negative fx dx minus fy df dy plus fz ds. Okay, so we know that fx equals x, fy equals y, and fz equals z. So all of these over here, all of the values for the coordinates are going to be constant, so we can determine that df dx is going to be 0 because the derivative of b constant is 0 and the derivative of 0 is obviously 0. And then same thing with y, df dy equals 0. So that makes it nice and easy for us. So this one specifically, this formula specifically, is going to be for this top plane where z equals b. Whenever we do the other sides, we will have to cast to the other, or project to the other planes, which will switch up this formula. But we'll take a shortcut around that, which I'll get to in a moment. So next up we have, so this is going to be one integral, and we're going to have to do this 3 times. The catch is that we can use symmetry to kind of shortcut this. Fortunately for us, the vector field is going to be the same through all 3 of these sides, so we actually only have to do this integral once and then multiply it by 3. So this integral is going to end up looking like, it's going to be integral from 0 to b, integral 0 to b, z dx dy. This is going to look like integral from 0 to b of z x from 0 to b dy. And then this can be further simplified to 0 to b of zb. And then again, dy. And then one more time is going to bring us to, I'll just save a step, and it's going to be zb squared. Now, since we're talking about this top axis, z is going to be constant, which happens to also conveniently be at height b. So what we can do here is we can actually substitute b in for this z, and we will get b to the third. Now, since there's three integrals, 1, 2, 3, and like I mentioned earlier, we can kind of use symmetry to shortcut this specific situation. We're just going to multiply it by 3 because we're looking at 3 sides. So we'll have times 3 for symmetry. And we're going to end up with 3b cubed, which is conveniently the same number we got up here for the volume integral. Next up, we're going to be looking at part B, which is going to be part of a cylinder. So, similar to the last one, we have our two starting functions. Del dot f is going to be similar to the way we did in Cartesian, but slightly different for cylindrical coordinates. So what we're going to do here is we're just going to plug things in again. So we have del f equals 1 over r, blah, blah, blah. So we're going to go equals 1 over r d dr of r squared. This fr comes from here. And then we're going to add 1 over r times 0, because there's no theta function in here, plus d dz of z. And this is going to simplify out. When we derive this, we're going to have 2r divided by r, it's just 2. So we'll have 2 plus 0 plus derivative of z with respect to z is obviously 1. So we'll have 1. This is, again, going to be 3. Okay, so we might as well start with the volume again. But we have to be careful this time because dv happens to be r dr d theta d z. So now we can translate this into an integral from 0 to h, 0 to pi over 2, and 0 to r of 3 dv, which is going to be r dr d theta dz. These bounds came from, because since we're looking at volume, we're looking to go from this origin out to r, around to pi over 2, and then up to h. So we're looking for 0 to h is that last one, 0 to pi over 2, because we're only looking at a quarter circle, and then 0 to r, because we're looking for everything in this range. Next up is just going to be some simplification. So h 0 to pi over 2 of 3 over 2 r squared d theta dz. And then we're going to be looking at 0 to h of 3 pi over 2, or oops, over 4. Over 4 r squared dz. And then this is going to finally simplify out to 3 pi over 4 r squared h. So again, oops. Again, we're going to make a note of this, and then we will come back to it after we complete this side. So next up for this one, again, the vector field is going to be pointing out from the center, the origin. So this left side, this back side, and the underside can be counted as 0 because they're all going to be parallel to the vector field. What we want to see is this top and this side. So we'll do this. Side 1 is going to be this top plate, and then side 2 is going to be this curved plate on the outside. So what we can do down here for this one is that, so n hat for the top is conveniently k hat, or z hat if for this notation. And then n hat for the curve is conveniently r hat. So, with that, again, we're going to have the same concept of the idea that we need to add integrals. So it's going to be integral of side 1 plus integral of side 2. So, we're going to be looking at the bounds for these, which is going to be, let's see, so the top integral is going to be double integral from 0 to pi over 2 and 0 to r of z, and it would be ds, but this has actually the same conversion as dv, so we're gonna do r d theta d phi, or not phi, dz, and then we're going to add the second integral, which is going to be 0 to pi over 2, 0 to h this time. And this time, we're going to be looking at r squared dz d theta. So, again, this so what these two come from is going to be z came from here. That's going to be the dot product of the vector field and n hat. So if we're looking at the top, it's just going to be k hat or z hat. So we're only going to be looking at this bit. So we have z, and then r d theta dz is going to be ds. And then same thing over here. We have, oh shoot, this is not going to be dz. It's just going to be d. Because we're just looking for the radius and the angle change for the top plate. And then for the side plate, we're looking for the angle and the height to change, but the radius is going to be constant. So that means that for this one, we can actually just pull this radius out front here, similarly to how we can pull this z out front here. So simplified, that's going to be integral z 0 to pi over 2. Here, let me 0 to pi over 2 of r squared over 2 d theta plus r squared integral 0 to pi over 2 of h, oops, not r, h d theta. Realistically, we could also pull out this r and this h, So this is eventually going to turn into equals z pi r squared over 2, or excuse me, over 4 plus, we're going to substitute big R in for little r here because it's going to be constant. So it's going to be r squared h pi over 2. Now, to make this a little bit cleaner, we can straighten this up. And also, we're going to substitute in here z equals h, because for that top plate, z is going to be at a constant rate of, or at a constant value, rather, of h. So we can now look at it like pi r squared h over 4 plus pi r squared h over 2, which can be simplified to 3 pi r squared h over 2. You'll notice that this is the same answer we got. Oops, not over 2, over 4. You'll notice that's the same answer that we got up here, which checks this one. And then lastly, for C, we have a sphere that we need to prove. So for this one, same as a cylinder, we have the two starting functions, and then we have del dot f is going to be, again, similar to what we had last time, but slightly different for spherical coordinates. So what happens here is that, luckily, we can just look at this function right here, and we can note, and you might notice that there's no theta and there's no phi. So this is going to be 0, and this is going to be 0. So we're only looking at this. So if we plug it in, we will find that we have this is going to equal 1 over r squared d dr of r to the 4th, r squared times r squared. And this will simplify to 4r. Next up, we're solving this triple integral volume. Again, we have to be careful of dv equals r squared sine phi, dr d theta d phi. So we can move this over here. This is gonna turn into integral from 0 to pi, integral 0 to 2 pi, integral 0 to r of 4r cubed sine phi dr d theta d phi. Again, it's going to be 4r straight in here, and then multiplied by the r squared coming from dv. It's going to be 4r cubed sine phi dr d theta d phi. Again, simplifying this out, we're going to get 0 to pi, 2 pi of r to the 4th sine phi d theta d phi. Again, if we simplify, we'll have 0 to pi of 2 pi r to the 4th sine phi d phi. We can pull out this whole thing because it's going to be constant relative to phi. And we can find 2 pi r to the 4th integral 0 pi of sine phi d phi. So this bit is gonna be a factor of 2. It's gonna be negative cosine of pi minus negative cosine of 0. This is going to be 1. This is going to be negative 1 technically, so 1 plus 1 is going to be 2. So we can do 4 pi r to the 4th. And then just like before, we're going to make a note of this. And we're going to move on to the surface area integral. So for the sphere, there's only one surface, so we actually only need one integral, or one double integral, rather. So we can write that out as 0 to pi, 0 to 2 pi. The reason we're doing this is because the radius is going to be constant around the surface, so we don't need to worry about that. That said, we're still going to have to bring in r to the 4th sine phi. It's going to be the same thing as up here. D theta d phi. So again, we can bring out, if we take this integral with d theta, it's just going to be 2 pi, and we can pull out r to the 4th. So we're going to have 2 pi r to the 4th times the integral from 0 to pi of sine phi d phi. And just like before, that's going to be a factor of 2. So we will end up with 4 pi r to the 4th. R equals r because, like I mentioned earlier, it's going to be constant around the surface, so we can just substitute big R in here, and we will end up with 4 pi r to the 4th, which is the same as this. And that is all 3 shapes proving the divergence theorem.